If we could build a space elevator, then you don't have to build a spaceship on the ground. Can transport materials to low Earth orbit, build a real spaceship, significantly reduce the cost of rocket launches. In 1895, Konstantin, the father of the Russian rocket Diakovsky, ever thought, why not build a tower that goes straight into space? If at the equator, build a cable that extends from the ground to space, it has a huge counterweight suspended from the top. Exploit the centrifugal force of the Earth's rotation, this cable will be as straight as a fishing rod. All they have to do is climb up that cable. You can reach space effortlessly. This cable to pass through the troposphere, the middle stratosphere, thermosphere, finally reaching geosynchronous orbit. At that height, the time it takes for a satellite to circle the Earth. Exactly 24 hours, synchronized with the Earth's rotation. So the top of the cable looks like it's nailed to the sky, not moving at all. This is not to put the satellite in orbit. Is it a natural crane? But Tsiolkovsky soon discovered a desperate truth. There is no material on Earth can make this cable. Why is that? Because of the weight this cable needs to bear. Unimaginable, a 36,000-kilometer cable. Just the weight of the rope itself, enough to tear yourself apart. Not to mention the elevator box cargo on it, personnel calculation results show. If you build a Range Rover out of steel, at an altitude of 10,000 kilometers, it will break due to its own weight. If you use carbon fiber, can barely make it to 20,000 kilometers. However, the story took a turn in 1991. Japanese scientist Shinami Fan, under an electron microscope, discovered something amazing: carbon nanotubes. How strong is this thing? It's 100 times stronger than steel. It is only 1/6 as dense as steel. 1 centimeter per square, in theory. Meter-thick carbon nanotube cable can lift 6,000 tons of weight, equivalent to putting a destroyer hanging on a rope as thick as a fingernail. Scientists have gone mad. They recalculated the feasibility of a space elevator. The result shows, if you can make a perfect carbon nanotube cable, space elevators are theoretically possible. But the longest carbon nanotubes we can make right now, only 55 centimeters. The space elevator requires 36,000 kilometers. This is crazy. Scientists, after all, industry-all-grade carbon nanotubes have not been developed yet. And here's what's even worse. These nanotubes can't just end to end. They have to be perfectly woven together. Strength loss of any interface could lead to the entire cable suddenly broke off in space and a 36,000-kilometer cable. If it breaks in the middle, the bottom half will be like a crazy python, hit the surface of the Earth. The top half will be like a runaway wild horse flying into the sky. The devastation of this disaster is enough to destroy a city. Are we just giving up? Not when scientists realized. Space elevator. When the launch cost can be reduced by a full 100 times. All the difficulties, it has become a technical problem that has not been solved yet. Let's do an even crazier account. The International Space Station weighs 420 tons. We launch them on rockets. The cost of light emission exceeds $150 billion. If there were a space elevator, it costs only $1.50 billion. This means that we can be in space, build a truly massive spaceship. More carrying capacity, we will be one step closer to alien colonization. Because assembling a spacecraft in space, there's no atmospheric drag. No need to consider takeoff weight. You can slowly build blocks, put the spaceship together, as big as you want, as much as you want. What's even crazier is space electricity. The counterweight platform at the top of the ladder, it's a natural rocket launch site at an altitude of 36,000 kilometers. Earth's attractive force is only 1/30th that of the ground. This means that the spacecraft requires very little thrust. Can leave the Earth, to the Moon, Mars, and beyond. Here it is. Scientists haven't really given up on the space elevator plan. They're just waiting for a breakthrough in materials science. In 2018, a team of researchers at MIT found that even in the lab, the most perfect carbon nanotubes ever made, its actual strength is only 1/5 of the theoretical value. Because of tiny cracks at the molecular level, it expands under stress, like a scratch on tempered glass. A touch, the whole piece of glass shatters into pieces. What to do? Scientists have come up with a hybrid weaving scheme. Carbon nanotubes as the backbone. The outer layer wraps the graphene film, prevent UV degradation. Middle interlayer-filled Kevlar fiber. As redundant protection, the outermost layer is plated with a reflective coating, protection against space radiation. Such a composite cable. Even with partial damage, it won't break immediately. It's like a tightrope. A few broken wires can continue to bear the load. And then there's a little tacked-out technical challenge: the power source of the space elevator climber. You can't have an elevator box full of cargo climbing up with hundreds of tons of fuel on your back. Might as well just use a rocket. Essentially, it's powered by electricity. The most reliable solution at present is laser power transmission. Building a giant laser array on the ground. 10 trillion watts of power. Laser beam tracking is aimed at the photovoltaic panel at the bottom of the climber, converting light energy into electricity. The drive motor drives the wheels up the cable. The theoretical efficiency of the system can reach 40%, means climbers can reach from the ground in 24 hours. Synchronous orbit, the speed is 1,500 kilometers per hour. But laser transmission has a fatal flaw: atmospheric absorption and scattering. Cloud water vapor aerosols can weaken the laser intensity. So, the ground station must be built in a dry area near the equator. Then why can't you just tie a cable to the elevator, charging without mentioning the weight? The longer the wire, the greater the resistance. 36,000 kilometers long. No single COBOL engineering on Earth. This exaggerated cable all the way to geosynchronous orbit. Energy loss and heat generation caused by resistance will burn itself first. It could even bring down the entire space elevator structure. Some people go even further. They believe that instead of challenging the Earth's space elevator in the first place, how about building a space elevator on the Moon first, then gradually expand to the Earth system? The reason for this is straightforward. The Moon's attractive force is only 16.7% of Earth's. The cable will experience much less tension, and the Moon has no atmosphere, unaffected by storms, lightning, and air resistance. The environment is also more stable, more suitable for long-term deployment of large space facilities. But lunar elevators aren't designed to bypass Earth's attractive forces. Key equipment and core materials in the early stage still have to be shipped from Earth. What's really changed is the subsequent mode of mass transportation. It doesn't usually connect to lunar synchronous orbit. It extends into the vicinity of the Lagrange point. Because of these areas, between the attractive force of the Moon and the centrifugal effect, it is easier to form a relative balance, suitable as a space transit node. This way, although it still has to pay a high Earth launch cost in the early stage, but as soon as this node is built, many future transportation missions can start from the Moon. This two-elevator strategy saves not the first step. It is the cost of repeated transportation over a long period of time. So, no matter what form the future space elevator takes, will greatly reduce the cost of human rocket transportation, will become a new path for humanity to explore the interstellar journey.